Welcome to Monoprotic acid-base equilibria. So let's consider a strong acid like hydrobromic acid. Suppose we want to calculate the pH of 0.10 molar hydrobromic acid. Let's start by writing out the reaction between hydrobromic acid and water. Namely, they react to form hydronium ion and bromide ion. Now, we know the pH is equal to minus log base 10 of the hydrogen ion concentration, which in this case will then be equal to minus log base 10 of 0.10, which gives us a value of 1.00. Now bear in mind that we haven't taken activity coefficients into account. And if we do, then the pH is 1.08. So now let's examine a strong base like potassium hydroxide. Suppose we want to calculate the pH of 0.10 molar potassium hydroxide. So we've got our dissociation of potassium hydroxide, and that's going to be virtually complete. So all of the potassium hydroxide we put in will dissociate into potassium and hydroxide ions, and that means that for us to determine the hydrogen ion concentration, that's going to be equal to Kw divided by the hydroxide ion concentration, which is 1.0 times 10 to the minus 14 divided by 0.1, which gives us then a value of 1.0 times 10 to the minus 13 molar. And then the pH is 13.00. And the pOH would then be 1.00. But now let's go with a more dilute solution. Let's calculate the pH of 1.0 times 10 to the minus 8 molar KOH. So again, we know that all of the potassium hydroxide is going to dissociate. So now we get the hydrogen ion concentration of 1.0 times 10 to the minus 6 molar, and then the pH is 6.00. But this clearly can't be right, because all we have in solution, other than water, is potassium hydroxide. So that's a base, which means we ought to have a pH that is alkaline. It ought to be a pH that is higher than 7.0, but 6.0 isn't higher than 7. So clearly we've done something wrong. But what did we do wrong? Well, what we did wrong is we forgot to factor in the hydroxide due to the autoionization of water. And this means that we need to use the systematic treatment of equilibrium. So we need to write our relevant reactions. We have our autoionization of water. We have our charge balance. We know that our cations are potassium ion and hydrogen ion. Those concentrations must be equal to concentrations of our anions, which is only hydroxide. We can also write our mass balance. We know that the potassium ion concentration must be equal to our concentration of KOH that we put in initially, which was 1.0 times 10 to the minus 8 molar. And now we have three equations, three unknowns, and now we can solve it. Now, we want to find the pH, so let's set the hydrogen ion concentration equal to X. And we know that the hydroxide ion concentration is equal to the potassium ion concentration plus the hydrogen ion concentration, which means we know that it's equal to 1.0 times 10 to the minus 8 molar, since that's the potassium ion concentration, plus X, the hydrogen ion concentration. And now we can substitute this value into the Kw expression. So we get Kw is equal to X times the quantity 1.0 times 10 to the minus 8 plus X, and we know that that must be equal to 1.0 times 10 to the minus 14, because that's the value of Kw. But when we do some rearranging, we get a quadratic equation, which we can then solve using the quadratic formula, and we get either 9.6 times 10 to the minus 8 molar, or negative 1.1 times 10 to the minus 7 molar. Well, clearly, negative 1.1 times 10 to the minus 7 molar can't be real, because we can't have a negative concentration for hydrogen ion, which means that our hydrogen ion concentration must be 9.6 times 10 to the minus 8. And when we plug that in for our pH, we get a pH of 7.02. And this pH is now reasonable, since 1.0 times 10 to the minus 8 molar KOH should be just very slightly basic. We don't have very much of our strong base in solution, so we shouldn't be shifting the pH much, and in fact, we haven't shifted it very far at all. So note that we now have three different regimes for calculating the pH of a strong acid or a base. When the concentration of the hydrogen ion or hydroxide ion is high, we can ignore the autoionization of water. When the concentration of hydrogen ion or hydroxide ion is low, we can ignore the dissociation of the added acid or base. And when the concentration of the strong acid or strong base is 10 to the minus 6 to 10 to the minus 8 molar, we must use the systematic treatment of equilibrium to solve this. So remember that the acid dissociation constant Ka for some generic acid looks like this. We've got Ka is equal to the hydrogen ion concentration times the conjugate base concentration, A minus, divided by the concentration of Ha, our generic acid. Now remember that for a weak acid, the reaction does not go to completion. That is, only a small portion of our acid is dissociated. Most of it actually exists as the HA form, the protonated form. That is, HA is going to be larger than A minus. And remember that the base dissociation constant Kb for a generic base, for our generic base reaction here, is Kb is equal to concentration of BH plus times the concentration of OH minus divided by the concentration of B, where BH plus there is our conjugate acid for our base. That's the protonated form of our base. And again, for a weak base, the reaction does not go to completion. So this value here, the concentration of B, is going to be larger than the concentration of the protonated form BH plus. Also remember that we can calculate the pK for our equilibrium constants. So the pKw is minus log base 10 of Kw, pKa is minus log base 10 of Ka, pKb is minus log base 10 of Kb, and so on. So remember that as K increases, the pK decreases. And you should remember from general chemistry that every acid has a conjugate base, and every base has a conjugate acid. And the relationship between Ka for the acid and Kb for the base is then this one, where we have Kw is equal to Ka times Kb. So let's look at a couple of examples. We've got formic acid. We'll dissociate into formate. So the acid is formic acid. Its conjugate base is the formate ion. For formate, formate is a base. It's a weak base. Its conjugate weak acid is formic acid. Now the Ka here is the Ka for formic acid, which in this case is 1.8 times 10 to the minus 4, which gives us a pKa of 3.744. And down here we've got benzoic acid. Again, if we take the proton off, then we're left with benzoate plus our proton. So benzoic acid is the weak acid. Benzoate is its conjugate weak base. Benzoate is a weak base. Its conjugate weak acid is benzoic acid. Now the Ka for benzoic acid is 6.28 times 10 to the minus 5, or a pKa of 4.202. Now let's calculate the pH of a generic weak acid HA given the formal concentration of the acid F and the Ka. So we have two equilibria. We have the dissociation of our acid, HA, into H plus and A minus, and we have our autoionization of water. The charge balance is the concentration of H plus is equal to the concentration of A minus plus the concentration of OH. Now the mass balance is the formal concentration of our acid is equal to the concentration of our protonated form plus the concentration of our deprotonated form. And so now if we write the equilibrium expressions for our earlier equilibria, we get Ka is equal to the concentration of H plus times the concentration of A minus divided by the concentration of HA, and we get Kw is equal to the concentration of hydrogen ion times the concentration of hydroxide ion. So we now have 4 equations and 4 unknowns, so we can go ahead and solve. But we're going to end up with a cubic function here, so let's make a simplifying assumption. For most weak acids, the concentration of hydrogen ion from the dissociation of the acid will be much larger than that from the autoionization of water. That is, the concentration of A minus is much larger than the concentration of OH minus, which means that our charge balance can then be simplified. If this guy is much larger than that guy, then we can basically ignore the second one, and that means that our hydrogen ion concentration is approximately equal to the concentration of our conjugate base, A minus. And now if we replace the hydrogen ion concentration with X, that means that our numerator here becomes X squared, and our denominator becomes F minus F. And now, instead of a cubic equation, now we have a quadratic equation, which we can solve much easier. Remember, the quadratic formula is not terribly difficult for us to use. The cubic formula is much, much more difficult. So note that once we find the concentration, we then need to go back and check our assumption to be sure that it's valid. The assumption should be valid so long as the pH is less than 6. Now, the fraction of dissociation, which we symbolize alpha of an acid, is the fraction of the acid in the deprotonated form. And we can express that mathematically like this. We have alpha, our fraction of dissociation, is equal to the concentration in the deprotonated form divided by the sum of the concentrations of the deprotonated form and the protonated form, which then, if we call the concentration of the deprotonated form X, it's then equal to X divided by X plus F minus X, which then these two X's cancel, and so our alpha there is X divided by F. Now the treatment of weak base equilibria is similar to that for weak acids. Instead of an acid dissociation, we have the base hydrolysis reaction, and we can then write Kb is equal to the concentration of BH plus, our conjugate acid, times the concentration of hydroxide ion divided by the concentration of our unprotonated base. Now, if nearly all of the hydroxide ion comes from the base hydrolysis and very little comes from the autoionization of water, and then we set the hydroxide ion concentration equal to X, then we can also set the concentration of our protonated form equal to X. And that then gives us the concentration of our unprotonated base is equal to the formal concentration minus the concentration of our protonated form, which is equal to F minus X. And that means that in our Kb, we can replace our terms here with X, so we get X squared on the top, and we get F minus X on the bottom. So again, we now have a quadratic equation that can be easily solved, although in this case, X now stands for the hydroxide ion concentration, not the hydrogen ion concentration. And similar to the fraction of dissociation for an acid, we can talk about the fraction of association for the base, which again is going to be symbolized with alpha. And this is now the fraction of the base that has reacted with water. This is the fraction that is protonated. And so alpha is then equal to the same X over F. Only now in this case, X represents the protonated form instead of the deprotonated form. So now let's turn to buffers. Remember that a buffer is a mixture of a weak acid and its conjugate weak base. The concentrations of the acid and its conjugate base must be within a factor of about 10, otherwise you won't get much buffering going on. You'll effectively have a solution of just whichever one is more concentrated. Now buffers are extremely important in many areas of science, including our bodies. Our bodies are mostly composed of aqueous solutions in which our proteins must remain within certain pH ranges or they will not function properly. In other words, buffers are incredibly important biological tools. So you can see from this schematic of different portions of the cell that there are different pHs at different sites in the cell. They range from a low of about 4.7 up to 8. And so in different parts of the cell, we need to have buffers to keep the pH in those parts of the cell different from the pH in other parts of the cell. So when we mix A moles of a weak acid and B moles of its conjugate base, then the moles of acid remains close to A and the moles of base remains close to B. So let's examine an acid with a pKa of 4.00, and we then know that pKb equals 10.00, and suppose we have a concentration of 0.10 molar. Well, we can write out our acid dissociation reaction, we can write out our Ka, and then we're going to replace the concentration of H plus and A minus with X, so we get X squared divided by F minus X. Now in this case then, X is 3.1 times 10 to the minus 3 molar, given the value of our pKa, and that means that our alpha, our fraction of dissociation, is 0.031. That is, the acid is only 3.1% dissociated. It's almost 97% still protonated. So suppose we have a solution of 0.1 molar of our conjugate base, A minus. And when we put that into water, then we have the base hydrolysis reaction occurring, and we can then write our Kb, which then ends up as X squared over F minus X, where X then is equal to the HA concentration or the hydroxide ion concentration. And that value is then 3.2 times 10 to the minus 6 molar, and then we have our fraction of association, alpha, is then equal to 3.2 times 10 to the minus 5. And now, if we mix the two, then Le Chatelier's principle predicts even smaller fractions of dissociation and association. And this is because in our earlier examples, we put in our acid, but we didn't put in any of our base, and that means that some of our acid dissociated into the proton and its conjugate base. But of course, as we add some of our base in with our acid, that's going to shift this equilibrium back to the left, which means that less of our acid is going to dissociate into its conjugate base. Likewise, if we start out with our conjugate base in a beaker and we pour in some of our conjugate acid, then we're going to shift the equilibrium back to the right. We will deprotonate some of the base that had previously reacted with the water. So let's rearrange the acid dissociation equilibrium expression. So remember, here's our acid dissociation reaction. Here's the equilibrium constant expression. So we have Ka is equal to concentration of H plus times concentration of A minus divided by the concentration of HA. Now let's take the negative log base 10 of each side. So we have minus log base 10 of Ka equals minus log base 10 of that fraction. And now we're going to take out the hydrogen ion portion of that. So we're going to have minus log base 10 of Ka equals minus log base 10 of the hydrogen ion concentration minus log base 10 of the A minus concentration divided by the HA concentration. And now you note that minus log base 10 of Ka, well, that's our pKa, and minus log base 10 of the hydrogen ion concentration, that's our pH. So that now gives us pKa is equal to pH minus log base 10 of the concentration of A minus divided by the concentration of HA. That is the ratio of our conjugate base to our conjugate acid. And now if we solve that equation for the pH, that gives us the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is pH is equal to pKa plus log base 10 of the base concentration divided by the acid concentration. Now note that this equation is an approximation. However, if we include the activity coefficients, then it's not an approximation, it is in fact exact, and that then would look like this. pH is equal to pKa plus log of the concentration of A minus times the activity coefficient for A minus divided by concentration of HA times the activity coefficient for HA. Now, we often make the approximation that the concentration of the acid and the base are what we have added to the solution. That is, they haven't reacted with each other significantly. That is, we normally don't bother to use the systematic treatment of equilibrium to solve for those concentrations. So let's examine what happens when we have equal concentrations of the acid and its conjugate base. Well, we know that concentration of HA must be equal to the concentration of A minus, and that means that in our Henderson-Hasselbalch equation, then this ratio here must be equal to 1 because those values are equal to each other. So now we have pH is equal to pKa plus log base 10 of 1. Well, log base 10 of 1 is 0, and that means that pH is equal to pKa. So if we have equal concentrations of our acid and our base, that means the pH of our buffer is going to be equal to the pKa of our acid. So let's look at a common buffer called tris, which is short for tris-hydroxymethyl-aminomethane. So the pKa is 8.072 for the conjugate acid of tris, and suppose we want to calculate the pH of a 1 liter aqueous solution prepared with 12.43 grams of tris, where the molar mass is 121.135 grams per mole, and 4.67 grams of tris hydrochloride with a molar mass of 157.593 grams per mole. Now the concentrations of our base, which is tris, and our conjugate acid of tris are then given here. So the concentration of the tris, our base, is 0.1026 molar, and the concentration of this conjugate acid is 0.0296 molar. Now, if we assume that what we mix stays in the same form, then we can plug these concentrations into the Henderson-Hasselbalch equation, and we get pH is equal to the pKa, 8.072, plus log base 10 of our tris concentration, 0.1026 molar, divided by our conjugate acid concentration, which is 0.0296 molar, which then gives us a pH of 8.61. Now note that the volume of solution is irrelevant because it cancels in the numerator and the denominator of this log term. Now, naturally, if we take this to the extreme and have an extremely dilute solution, then the autoionization of water becomes more important, and it will become more significant than the buffering action of our tris. So this only obviously works at moderate to high concentrations of our buffer solution. If we dilute it more, then we essentially just have almost pure water. But so long as we remain at reasonable concentrations, we can then ignore the volume and thus ignore the autoionization of water. And that then means that we can change from our Henderson-Hasselbalch equation involving concentrations, we can then express it instead in terms of moles of our base and moles of our acid that we have added to our solution. So now let's add 12.0 milliliters of 1.00 molar hydrochloric acid to our buffer that we just prepared, and let's calculate the new pH. So when a strong acid is added to a weak base, they react completely to give the conjugate acid of our weak base. So we can go ahead and calculate the number of moles of hydrochloric acid that we've added, and that ends up being 0.0120 moles. So let's make an ice table to determine the new amount of tris and tris hydrochloride. So remember, an ice table is I stands for initial, C stands for the change in concentration, and E stands for at equilibrium, what do we have remaining. So initially we have 0.1026 moles of tris. But if we've added 0.0120 moles of hydrochloric acid, then we're going to end up with 0.0906 moles of tris after reaction. We started out when we had 0.0120 moles of hydrogen ions in solution from our hydrochloric acid. All of it's going to react, so we'll have none left. Now this isn't really zero. Obviously, we still have some hydrogen ion around, but we're going to call it zero for the sake of this reaction going to completion. And then we started out with 0.0296 moles of our conjugate acid, we're going to add another 0.0120 moles, and that gives us now 0.0416 moles of our conjugate acid. And now we can plug our values into our Henderson-Hasselbalch equation. So we have pH is equal to pKa, 8.072, plus log base 10 of the ratio between our concentrations. So 0.0906 molar divided by 0.0416 molar, and that gives us a pH of 8.41. So this pH of 8.41 is lower than the pH of 8.61 that we had before we added the hydrochloric acid, but it hasn't changed much. It's only changed by 0.2. So now let's see what would the pH be if we had added that 12 milliliters of hydrochloric acid instead to distilled water, instead of adding it to our tris buffer. Well, in this case now we know the hydrogen ion concentration is 0.0120 moles of hydrogen ion divided by 1.00 liters plus our 0.0120 liters, which then gives us a concentration of 0.0118 molar, and then the pH ends up being 1.92. So why did the pH not change very much when we added the acid to the buffer? Well, the answer to that is that nearly all of our acid reacted with our tris. Not all of the acid, obviously, but most of the acid. Almost all of that acid reacted with the tris. So let's calculate what percentage of our hydrochloric acid that actually reacted with our tris. So we know the pH changed from 8.61 to 8.41 upon addition of the hydrochloric acid. So let's find the hydrogen ion concentration in each case and determine the change between those two. Well, we know the pH equals minus log base 10 of the hydrogen ion concentration. So to find the hydrogen ion concentration, we need to take 10 raised to the power of negative pH. Well, for the pH of 8.61, that gives us a hydrogen ion concentration of 2.45 times 10 to the minus 9 molar. For a hydrogen ion concentration in the case of pH of 8.41, we get a value of 3.89 times 10 to the minus 9 molar. And that means that our change in hydrogen ion concentration is then 1.44 times 10 to the minus 9 molar. And now let's calculate the number of moles in that change. So we have a change of 1.44 times 10 to the minus 9 molar for our hydrogen ion concentration. And we have a volume of 1.012 liters, which gives us 1.45 times 10 to the minus 9 moles of hydrogen ion did not react with our tris. Now, the number of moles of hydrochloric acid added was given here, and that was 0.0120 moles. So now let's calculate the percentage of the hydrochloric acid that did not react, and then use that to calculate the percentage that did react. So we have 1.45 times 10 to the minus 9 moles divided by our 0.0120 moles times 100%, which gives us 1.2 times 10 to the minus 5% of our hydrogen ion that was left unreacted, and then 100% minus that value gives us 99.999988% of our hydrogen ion reacted. So as you can see, almost all of our hydrogen ion reacted with our tris buffer. And this is why buffers are so effective at resisting changes in pH. Now let's find how many milliliters of 0.500 molar sodium hydroxide should be added to 10 grams of tris hydrochloride to give a pH of 7.60 in a final volume of 250 milliliters. Now the number of moles of tris hydrochloride are given here, and that value is 0.0635 moles. Now again, let's make an ice table to determine the needed amount of tris hydrochloride and sodium hydroxide. So we start out with 0.0635 moles of our tris hydrochloride, our protonated form. We know that we need to add some amount, X, of sodium hydroxide. We know that all of the sodium hydroxide is going to react away, so the amount that will react there is minus X. That means we'll end up with 0 moles of our hydroxide left over. Now obviously we won't actually have 0 left in solution. We'll still have some from the autoionization of water, but we're going to say that all of it is react. And that means that the amount of tris hydrochloride that remains is 0.0635 moles minus X. And of course over here, if we start out with none of our tris buffer, that means that then the value will increase by plus X, and that means we'll end up with X of our tris buffer left over. And so now if we plug these values into our Henderson-Hasselbalch equation, we have here our Henderson-Hasselbalch. We plug in the pH of 7.60, the pKa of 8.072, and then we plug in X for our base concentration and 0.0635 minus X for our acid concentration. We can then combine our pH and pKa on one side, so we get minus 0.472 on the left, and this log term on the right. We can then raise 10 to the power of both sides, and that gives us this exponential on the left and this fraction on the right. We can then move the denominator over to the left, so we have 10 raised to the negative 0.472 times the quantity 0.0635 minus x, that all equals x. And then we can move the x's onto the same side. And when we solve for x, that ends up giving us 0.0160 moles. And now we can calculate the volume of our 0.5 molar sodium hydroxide that contains that 0.0160 moles of sodium hydroxide. And when we work out the dimensional analysis, that works out to be 32.0 milliliters of sodium hydroxide that we need. So that was in theory. But now let's talk about when you prepare a buffer in real life. Well, if you really want a buffer with a pH of 7.60, you wouldn't calculate what to mix, as that will not give you exactly the pH that you want. Now, there are a number of reasons why you can't simply weigh out the calculated masses and mix them. One reason is that your distilled water will absorb some CO2 from the air and will thus not have a pH of exactly 7.0. Another is that we haven't taken into account the ionic strength and the activity coefficient. So instead, what you should do is weigh out 0.100 moles of tris hydrochloride and dissolve this in a beaker containing around 800 milliliters of distilled water. Then monitor the pH using a calibrated electrode. Then add sodium hydroxide from a burette very slowly until the pH is exactly 7.60. And then transfer the solution to a volumetric flask and wash the beaker a few times. The washings should go into the flask, and then dilute to the mark and mix. So now let's talk about buffer capacity, which we symbolize with a beta. Buffer capacity is a measure of how well a solution will resist changes in pH when a strong acid or strong base is added. So mathematically, we write it this way, where beta is equal to dCB over dpH, or minus dCA over dpH, where these CB and CA are the number of moles of strong acid or strong base per liter needed to produce a pH change of 1. That is, the CA, the CB, and CA represent the concentrations of base and acid that you have to add in order to get the pH to change by 1 unit. Now, the buffer capacity is highest at pH near the pKa value. So the major reason why the calculated pH of a buffer is not equal to the actual pH is because the ionic strength is not 0. And that means that the activity coefficients are not 1. But the buffer pKa also has a significant dependence upon the temperature. For example, the pKa of tris changes by negative 0.028 per degree near room temperature. And this means that a tris buffer with a pH of 8.07 at 25 degrees C will have a pH of 8.7 at 4 degrees C and a pH of 7.7 at 37 degrees C. So let's examine another reason why the calculated pH may not be the observed pH. So suppose we mix F number of moles of HA and F number of moles of A minus, where that A minus is in a salt including sodium ions. Now the relevant equilibria then would be the acid dissociation of our HA and the base hydrolysis of our A minus. Now the mass balance is then the formal concentration of our HA plus the formal concentration of our A minus is equal to the concentration of HA plus the concentration of A minus. And the charge balance is then the hydrogen ion concentration plus the sodium ion concentration is equal to the hydroxide ion concentration plus the concentration of A minus, our conjugate base. Now, we know that the concentration of sodium ion must be equal to the formal concentration of our base, A minus. And if we substitute this into the charge balance and solve for the concentration of A minus, we then get this guy, where we have concentration of A minus is equal to the formal concentration of A minus plus the hydrogen ion concentration minus the hydroxide ion concentration. And now, if we solve the mass balance for the acid concentration, HA, and substitute that for our base concentration, A minus, well, we're going to start out with our mass balance here. We're then going to solve it for HA, and now we can take what we had on the previous slide for our concentration of A minus in terms of hydrogen ion concentration and hydroxide ion concentration. We can then plug that in here for A minus, and that then gives us our acid concentration of HA is equal to the formal concentration of HA plus the formal concentration of A minus minus the quantity, formal concentration of A minus plus the concentration of H plus minus concentration of OH minus. And then of course we've got this guy in here twice, and so those will cancel, and we end up with concentration of HA is equal to the formal concentration of HA minus the concentration of H plus plus the concentration of OH minus. And now we have two equations telling us the concentrations of our acid and our conjugate base. Now, Thus far, we've assumed that the concentration of HA is pretty close to the formal concentration of HA, which will only be true when the formal concentrations are large compared to the concentration of hydrogen ion and hydroxide ion. That is, we've got these two equations. As long as the hydrogen ion concentration and the hydroxide ion concentrations are small, then these terms drop out and the concentration of HA is approximately the same as the formal concentration of HA, and the concentration of A minus is approximately the same as the formal concentration of A minus. But if either the formal concentration of HA or the formal concentration of A minus is small, or if the hydrogen ion concentration or hydroxide ion concentration are large, then the approximation we make here is not going to be valid. And note that we can ignore the hydroxide ion concentration if the solution is acidic, or we can ignore the hydrogen ion concentration if the solution is basic. So suppose we want to calculate the pH of 0.0100 moles of HA with a pKa of 2.00 and 0.0100 moles of A minus dissolved in water to make 1 liter of solution. Now the solution is acidic because the pH is approximately equal to the pKa because we have a 1-to-1 ratio of our acid to our conjugate base, and that means that we can ignore the hydroxide ion concentration because it's so small. And so if we set the hydrogen ion concentration equal to X, we then get the concentration of HA is equal to the formal concentration of HA minus X, which is 0.0100 minus X, and we get the concentration of A minus is equal to the formal concentration of A minus plus X, which is 0.0100 plus X. And if we now substitute those into the Ka expression, we get Ka is equal to X times the quantity 0.0100 plus X divided by 0.0100 minus X, and we know that that value must be equal to 10 raised to the negative 2.00. So when we do some math, we ended up with a quadratic equation here, and when we use the quadratic formula, we get a value for X of 0.00414 molar, which gives us then a pH of 2.38. Now, note that the Henderson-Hasselbalch equation predicted a pH of 2.00. And in this case, HA is too strong and the concentrations are too low for HA and A minus to equal their formal concentrations. Note that the Henderson-Hasselbalch equation, including activity coefficients, is always correct because it's simply an algebraic rearrangement of the Ka expression. So with the approximation of the Henderson-Hasselbalch equation, we got a value of 2.0 for our pH, our predicted pH. But if we had included activity coefficients, we would have gotten the correct pH value of 2.38, and that was monoprotic acid-base equilibria.